So what I'd like to look at is assume that you're given an arbitrarily large number of heuristics of any type of heuristics, cheap heuristics, expensive heuristics, delete, relaxation heuristics, PDBs, anything you want, and lots of them. And now what you want to do is you want to select from that collection of heuristics a subset that will most reduce the time it will take for your problem solver to solve a specific problem. And not only that, but you want that selection process to be cheap. Okay. So when we say that we want to find that best combination, there's really two sides to this. One is we want the combination to reduce the time it takes to solve the problem, but we want the process of making that selection to be cheap. Because what we want is the total time from the time you give the problem to the problem solver to the time the problem solver returns the solution to be what you're trying to minimize. Okay, so it's not just making the problem solving time short, but it's also taking into consideration if you're generating PDBs or generating heuristics that are tailored to that problem, it's the time that it takes to do that. It's the time it takes to now make this selection of that subset of heuristics. And then now that you've made your selection, now you'll go and solve the problem. So you want that sum of all those times together to be, sort of reasonable. Yeah.
Your timers must be on.
Okay, now, if I can. So do I go down? How do I get? Context. All right. So I will probably try and keep it from going. Anyway. Smart systems. So we have this. We now have the ability to create this arbitrary number of heuristics. We want to select some subset of those heuristics that we're going to max over. And basically, the problem is that predicting the performance of a combination of heuristics is not predictable from looking at the performance of each individual heuristic itself. I can't say that this heuristic has a certain branching factor, that heuristic has a certain branching factor, and now I can tell you what the branching factor for the combination is. What you have to do in order to figure out what the branching factor is you have to look at the combination, not just the individual components of that combination. And that means that your analysis, your process, potentially at least, the cost of making that selection is going to grow exponentially with the number of heuristics that you have from which to select. Okay, so what we want to do is we want to use an explicit runtime formula that will predict how long it will take for that combination to solve the problem. And we want to be able to do that and avoid this sort of combinatorial explosion that comes with having these combinations of heuristics that we need to consider. Good. All right. So we've been here already. God, sorry. I haven't had much sleep in the last few days. So anyway, this whole thing is all about finding the right trade-off between the quality of that combination that we find and how much it costs to find that combination. Okay, so how are we going to determine the quality? Well, determining the cost of the selection process is trivial. You know how to add time together. Okay, but how do you evaluate the quality of your selection? Well, I don't really know a good answer. But the best answer I know is you compare it against other systems that are in some sense comparable. Okay, so that's what we're going to do. We're going to see, how well our system, which we call RIDA. Yes, I'm going to be there. And we're going to do it on the 2011 IPC Deterministic Optimization Track Domains and Problems. And all these systems that we're going to use to compare are going to use exactly the same sort of planner. They're going to use fast downward with A star. The only difference between the systems are going to be the the selection of heuristics that they use. And we'll talk about how we do that, and the comparisons are based on the 192 problems out of the 280 available that were solved by at least one of those systems. So for each problem, RIDA is going to have an initial base of 45 different heuristics from which to choose. 3 of them, LM-cut, IPDB, and HMax are sort of standard what you would expect. We did a little funny thing with Edelkamp's genetic algorithm PDBs. Instead of just returning the best one, they returned the top 21 candidates that they found within their time constraints. So we got 21 disjoint heuristics and top 21 non-disjoint heuristics. So the systems that we're going to be comparing against, fast downward doing A star, where the heuristic is selected by IPDB, where Edelkamp's genetic algorithm PDBs non-disjoint maxes over those top 21, and where the disjoint maxes over the top 21 that it has. LM-cut is being used online, HMax is being used online. And then sort of naive selections where we just take the max. So one of the systems will just do no selection at all. It'll just max over all 45. Another one is going to randomly choose from those 45 at each node. And then there's RIDA, which is going to select some subset of those 45 that it will use at all the different nodes. So RIDA is going to use a runtime model to decide which combination of heuristics, which subset of heuristics will most reduce the time it needs to solve the problem. And basically, so the time that it takes that combination C to expand, to generate all the nodes with a given F value is approximately equal to the number of nodes that have that F value times the time per node costs using that combination. So it's a really trivial formula, nothing new there. And so basically there's 2 variables that depend on which combination we're talking about: the branching factor, the heuristic branching factor for that combination, and the time to evaluate a state using that combination of heuristics. So RIDA uses that formula on the combinations that it's interested in to select which one of those is going to most reduce the search time. And of course, since there's variables in there, it has to find values for those variables, for the different combinations, etc. And some of those it can measure at the beginning, like it can measure what the time it will take to generate a node, by doing random walks through the tree, and then finding the average time, over all those nodes. So there's various values that we can compute very easily. Some, however, we actually have to wait until we've gone through and done some problem solving for this specific problem. We have to go through sampling through the search tree and find out certain things like what is the branching factor, etc. Okay, so that's part of the process of making the selection, is going through and finding out what the values of the variables is. Now, what we're going to look at right now is trying to assess the quality of the selection that is made by RIDA and the cost it has for doing that selection. And we're going to look at the quality along 3 different ways: how much it reduces the search time, how many problems it can solve, and what is that total time to do everything. So here, what we see is the ranking of the systems for how long it takes on average to solve those 192 problems individually. Right. So there was a name problem, and so I had developed the tables before I found out that we had to change our name. So in all the text, in the paper it's RA star. In the rest of the talk it's RIDA, because that's what the system's called in IPC this year. Okay, so wherever you see RA star, it's RIDA. Okay, so RIDA takes 88 seconds on average for each one of these 192 problems. And there's the average times for the other systems. RIDA does okay. Here, because it takes less time, what you would expect is that it's going to solve more problems than the other systems, and that's what it turns out as well. RIDA solves 187 of those 192 problems. And the next system, which are the EDLCAMPS GA PDBs, solve 173, 172. And then Max comes in with 170. And then IPDB with 164, and so on down the line. Okay, so if we look at total time, so what RIDA did for reducing the search time per problem, it was doing well. Solving more problems than the other systems, it was doing well. When we look at the total time, it's not doing so well. It's right in the middle, and this makes us worry, because what we want is we're concerned about the total time, not just that it can reduce the search time, because we want to reduce the time from giving the system the problem to getting the answer back. That's the time we really want to reduce. So that's what that was looking at. So this makes us sort of worry. So what we do is we look at the breakdown of where the time is going in RIDA. And what happens is it takes 70% of its total time, to solve a problem in just generating the PDBs. Then it takes less than 1% of the time to decide on what combination of those heuristics it's going to use to solve the rest of the problem. Okay, so it being in the middle of the league table there is not a reflection on how expensive the selection process is. It's how expensive it is to generate everything of all those PDBs. Okay, so as far as sort of determining, can this approach select good combinations? And yes. Oh. Can it select good approaches, good combinations, and do it cheaply? I think the answer is yes. And the question is really, in essence, this is a combinatorially expensive problem. So how can we do it cheaply? And that's what we're going to look at next. So first, what we want to do is identify where the costs can blow up. Okay, and they can blow up in two different areas. So one area is that the actual cost of computing the runtime for a combination can grow exponentially with the number of heuristics that we're selecting from. Okay, and basically why that happens is that in the cost of finding the value for the branching factor for a combination, that actually is exponential with respect to the number of total heuristics that are available that we're looking at. Okay. The other place where we can get this combinatorial blow-up is, well, if we're going to look at 2 to the 45th combinations, if the number of combinations we're going to look at grows exponentially with the number of heuristics in the set, that's a problem. Okay, so we really have to find ways of limiting these. Okay, so which variable value is likely to be really expensive to compute, to be exponential with respect to the number of heuristics in our set? Well, it's the branching factor. Basically the branching factor is that we're doing is the ratio of the nodes with some current F value to the number of nodes that have the previous F value, and we do a ratio of them in a particular way, and that will give us the F value. Okay, so what we want to do is we want to reduce the cost of getting those counts. Okay, so basically the idea is that when we're going to compute those branching factors, we're going to break the computation into 2 stages. One stage is basically gathering all the data that we need to compute the branching factor for any combination, any one of those 2 to the 45th combinations. And then the second phase is after we've gathered all that data. By that time, we will have explored a fair bit of the problem, and we'll know which heuristics are worthless, and we'll get rid of them, and we'll use the data to compute the branching factors for the combinations we're interested in. Okay. So, when we're gathering up the data that we're going to use, there's 2 possible sources of costs there. One is where are we getting the data? So, cost is where we're getting the data and what we count. Okay, how many times we count. So, basically, we get the data from a single search tree. Regardless of how many heuristics, how many combinations we're interested in, we only grow one search tree. And that search tree is at most the size of the brute force search trees. And usually, it's really a lot smaller. Okay, so and we only do 1 add per node, regardless of the number of heuristics that are involved in combinations. So the time to get the data, to gather the data, turns out to be constant, really constant. Okay, now using the data to predict the runtimes, there's 2 things. One is the number of runtimes that we're going to compute, and the other is the cost of making that computation of that runtime. You know, both of those can be very expensive, and it turns out that while we're doing the sampling, we're getting rid of the weak heuristics. So typically, we start off with 45 heuristics. We reduce that to 15 heuristics. So we go from trillions of combinations to a few thousand combinations. Yeah, 32,000. Okay, so big reduction. Okay, that's really important. And that reduction reduces how expensive it is to compute the branching factor. Okay, the other really important thing for reducing the cost of this is that we cheat. And we cheat by saying we're only going to spend so much time computing these, predicting these runtimes. And based on that, when we run out of time, we're going to stop predicting. And I've run out of time. So basically, we start with singleton combinations, doubles, triples, and so on. And at some point, we run out of time. But it turns out with, having reduced the number of combinations from 2 to the 45 to 2 to the 15 combinations, we're often able to compute all of those 2 to the 15 combinations runtimes. And so that's good. Okay. Let's see. Anyway, so basically, the cost for computing and making that selection turns out not to grow exponentially, but is sort of a constant. Okay, there's lots of people who have done, good stuff, interesting stuff. Chris Rayner and company look at subset selection. They, however, don't worry about runtime. What they look at is information loss, and they can, basically are trying to reduce the size of the search tree. There's a lot of relevant, research in how do you combine heuristics, maxing, random, cell max, lazy A star, rational lazy A star, and then there are systems that hide their selection process in sort of the construction of the heuristic. So like Edelkamp's genetic algorithm, PDB, while it just comes up with one heuristic, it's really searching through the space of heuristics. and combinations of heuristics. And the same is with true of IPDB. Okay. Summary. I think we have a case that the approach works. I really haven't given you any details, so it's all magic, and I'm really sorry about that. But as you see, 18 minutes is really a short amount of time. I can't believe it. That other guy really did well. Anyway, so I guess I'm kicked off.
Thank you very much, Mike.
That's it.
Okay, so we have some time for questions magically.
Okay.
So one quick question first. I didn't quite get, do you make the heuristic selection on a per node base? Or
No. So we just select a subset, and then, that's another aspect. So like we could do cell max or whatever at the individual nodes, but we would select the subset of heuristics from which cell max would make its selection.
Okay. Another question. Your results look quite impressive. So did you compare it to you just using a portfolio of the individual heuristics?
No.
I actually did once.
Oh, okay.
The difference was 3 or 4 heuristics, but the big difference here between portfolio approach and this is a portfolio chooses singletons. It cannot combine. So, for example, PDBs, we all know a few PDBs is better than one. A portfolio can never do that. So we here we can combine heuristics constructively, and they can help each other. IPDB and LM character, you would normally put them together. In some cases, they cover each other's blind spots. Like that, basically. That's the main difference in the portfolio. Performance-wise, depends what you put in.
Thanks.
Anyone got another quick question? Okay, well let's thank the speaker again. Thank you.